Today we're going to talk about empirical equations. We'll talk about what that actually means. For pipe flow. And we'll talk about minor losses as opposed to major losses. And our learning objectives. We'll calculate pipe velocity, pipe flow velocity, or head loss using two empirical equations known as, the first one is called Hazen Williams. And the other is called Mannings. These are two different equations that we'll use. We're going to discuss the relative accuracies of these. Compared to what we'll call, there's two ways you could say an analytical equation or a theoretical equation, we'll just say, or we could say physics-based. Like Darcy-Weisbach, which is mostly physics-based. And then finally, we will define and calculate minor losses in pipe flow. And these are losses that occur, so energy losses that occur due to, for example, bends, contractions or expansions, and valves. All right, so we've, up to this point, we've had the energy equation. And we've had the Darcy-Weisbach equation, right? Where our head loss is equal to this friction factor, length over diameter, v squared over 2g. And this is essentially a physics-based equation. It's got this friction factor, which is based on experimental data, but by and large, we call this a physics-based equation. It's a little more challenging to use because often when we use it, we have this iterative approach. We have to go to the Moody diagram or plug in some value for the friction factor. It can be cumbersome in some cases. And before we had, modeling programs and spreadsheets, we use these kind of approximations. And so I'm going to introduce this concept of empirical equations. What does that mean to you, empirical versus theoretical or physics-based? It's based on something and lots of something, and that something is data or observations. So kind of empiricism is we're gaining knowledge or doing scientific inquiry based on making observations and analyzing those observations. So we'll just say this is based on data or observations. And often it's kind of just like fitting a line to some data. So for example, We could have a velocity, something that we're measuring, that's something that we're interested in estimating for ultimately for flow rate, right? And then we have some variable that we're interested in. That could be for a pipe, it could be the slope, could be the, we'll introduce this term a little bit more, or define this term a little bit more about hydraulic radius. This is an aspect of the pipe. This is equal to the area of the pipe. We'll just do this real quick. We'll define this a little bit more when we talk about the Mannings equation. The wetted perimeter is just the perimeter that's in touching the water. And of course, the area is the cross-sectional area. This is a parameter that gives you that, when we talked about energy loss in pipes, thin pipes versus big pipes, there's going to be more energy loss for something that has let's see, in the Mannings equation, velocity is equal to 2/3 of hydraulic radius. So a smaller hydraulic radius basically means that the wetted perimeter is greater relative to the area. There's more water touching, experiencing friction on the pipe. So a narrow pipe, small hydraulic radius, big pipe, large hydraulic radius. So this gets at how much water is touching the pipe and experiencing friction. And so we could say that we could measure these things in a pipe and pipe flow or open channel flow and calculate the velocity and get a bunch of data. And often we take the logs of these. This is not a real equation that I'm writing out here, but I'm just kind of showing it as an example. And by taking the logs of these views, often they have a nonlinear relationship. So in reality, this relationship might look like that, or like that, or something like that. So if we take the logs of them, and then in log-log space, often we have a straight relationship or a line, so you can fit a straight line to those data. And by doing so, we can back calculate the slope or exponent of this line, intercept. So coefficients, essentially. So we collect data, and we have our independent variables. So things that we can measure easily. We can measure the length, we know the diameter, calculate hydraulic radius. So these are independent variables, and then we also get our dependent variables. In this case, it would be velocity. This is the thing we're trying to calculate. So now we have all this kind of XY data. Fits a line, and this could be linear or nonlinear. And this, by fitting that line, this is a statistical exercise that you do. We'll actually talk about linear regression and statistics, and you get coefficients. So in the case of, there's one equation that, I don't know if we'll use it in class, but it looks like this. V is equal to some coefficients, hydraulic radius to the A, and then slope to the B. And so these are our coefficients right here that we would calculate from a regression type of analysis, a statistical analysis. Once we have these coefficients, then all we need to do is calculate our pipe property, our slope, and then we can estimate velocity based on this equation. This equation is bounded by our data. So we don't want to extrapolate beyond that. So we can calculate V or Q or whatever else elsewhere using the empirical equation. from this statistical analysis based on new independent variable values and these coefficients. But we're not going to, for example, if my slope at this bottom point was 0.0001 and up here it was 0.1, then if my pipe falls out of that range or my circumstance falls out of that range, I don't want to extrapolate beyond that because the data are only valid within the values of our independent variables. So we do this all the time in hydrology, where we have the peak discharge in the stream with a 1% probability of happening in a given year as a function of the drainage area and the slope. And I'm going to go look at all the USGS gauges around and get the statistic or the data from that, and then make a regression like this. But I can't use it for drainage areas or slopes outside of my data, the original data set. So this is how empirical equations happen. Engineering, hydraulics, hydrology, environmental engineering, even materials is rife with empirical equations. Anytime you see things with weird exponents or the units don't necessarily work out, it's from some sort of analysis like this. It's a regression type of analysis typically, with kind of an experimental type of setting. So let's introduce our empirical equations. The first one is a Hazen Williams. And it's got a couple different forms. It's got a form for velocity and it's got a form for head loss. And the trick with our empirical equations is that they depend on what unit system you're using, and so the coefficients will change. So in British gravitational or US units, it is velocity of flow is 1.318 times this coefficient, which is based on your pipe properties. And times the hydraulic radius to the 0.63 times the slope to the 0.54. And this has units of feet per second. We can look this coefficient up in table 3.2 in your book, and it's going to give you these Hazen Williams coefficients for different types of pipes. In SI, it is just a different coefficient, 0.849 times CHW, and then the exponents don't change. Why don't the exponents change if we're in a different unit system? Yeah, so if we were to say, for example, the hydraulic radius, this would be in feet and this would be in meters. There's going to be a difference in these numbers, right? But if I exponentiate them to 0.63, you just get a constant out of it, right? It's not a variable, it's just a constant. So that constant is accounted for in these coefficients. All right, so hydraulic radius, I defined it earlier. It's area over wetted perimeter. I think your book might write it area over P for perimeter. And for a pipe, for a circle, this is pi d squared over 4 divided by 2, or sorry, divided by pi d, right? So this ends up being d over 4. So that's pretty easy to calculate with your pipe. So table 3.4 gives you another version of the equations that we're talking about today, and this is in terms of head loss. This might be a little more useful to you. And what it says is head loss takes the form of, well, first I'll write out what the equation is, and then I'll give you the kind of generic formula. So for British gravitational, I'll just give you this one. You can look up the others in the table. Is we get 4.73 times the length of the pipe all over d to the 4.87 are coefficients. So 1.85. And this is times Q raised to the 1.85. So it's kind of similar to the Darcy-Weisbach equation. You've got length, you've got diameter, you've got velocity in here in terms of flow rate, right? So you can calculate this directly without, if you know flow rate, without having to do the Moody diagram and all that. So it makes it a little bit more straightforward. The table 3.4 is a little funky, but it basically just says HF is, it gives you a lot of different equations, empirical equations. It even gives you the Darcy-Weisbach equation. But it says HF is equal to some coefficient K times Q to the M. And what I gave you right here is that K value. And then this is your M. So just a couple other notes for Hazen Williams. So do not extrapolate. Beyond the input data. The data that went into making that equation. And for that, we have, we need, so your diameter must be greater than or equal to 5 centimeters or 2 inches. And then your velocity less than or equal to 3 meters per second or about 10 feet per second. Right here. These are the sort of, what do you call it, values for which the Hazen Williams equation applies. Meaning the data that they used involved situations where velocity was less than this and diameter was greater than this. And that gets back at up here where they did some sort of laboratory tests to come up with those parameter values, and our velocity and diameters were within some bounds or above some bounds. Okay, one other note, I talked about hydraulic radius, but let's talk about slope. Often we approximate this by the actual slope. Delta Z, or sorry, delta Z over length. Change in elevation over length, right? Rise over run. But that is, if you look up at the energy equation, what we're actually interested in is what's called the friction slope. which is equal to, so we denote that as S sub F, and that's equal to your change in energy over a length. And we gave an example of that, I think, last week, where we said the maximum head loss over this 2 kilometers of pipe is 2 meters. So you could calculate the friction slope as 2 meters of head loss over 2,000 meters of pipe. And that would give you your friction slope. All right, I'm going to introduce one more, and then we'll do an example together. So the other, we'll use this actually, it's not often used in pipe flow, but it can be as an approximation, Mannings equation. It's mostly used in open channel flow. That's where it came from originally. It's pretty similar to the Hazen Williams. The Hazen Williams was actually developed for pipes, but we get velocity is equal to 1 over n. This is the Mannings coefficient. Or sorry, 1.49. This is for British gravitational. Hydraulic radius to the 2/3, and then slope to the 1/2. And this gives you velocity in feet per second. And then for metric, we just get 1 over n times s to the 1/2. And then in terms of head loss, if we do it in this form, we get, just for British gravitational, I'll give you. And this again is table 3.4. We get 4.64 n squared L over d to the 5.33 times q squared. So n is called the Mannings roughness coefficient. And it is in table 3.3, which I think you have in your handouts. Let's take a look. Yep. So on the second page of your handouts, you can see some values for Mannings roughness. They give you some ranges. It looks like it ranges for pipes 0.009, 0.025, something like that, 0.3. So it's got different units. The Hazen Williams coefficients are in the hundreds. We'll note that the Mannings roughness coefficient is in the denominator. And so a bigger value means it's rougher. And this is smoother. I like Mannings equation because this is a little more intuitive. A bigger number, more energy loss, essentially. A bigger value means we get a smaller velocity, right? But it's the opposite for Hazen Williams. On the second page of your handout, there is a Hazen Williams table. And you can see for really smooth stuff, it's in the 150s. And for rougher stuff, 40-year-old cast iron, you're down there in the 60s, 70s, and 80s. Okay, so let's do an example. We're going to compare the Darcy-Weisbach equation result with these empirical equation results. Then we'll take a stretch break. Empirical example. Okay, here's our little reservoir. We've got a pipe flowing to another reservoir. I'm going to do a lot of these. And I think this is the same as a type 2 problem that we did last time. And this is cast iron. And so our task, as before, was to find Q. And we're going to do it. We're going to do it Darcy-Weisbach, which we already did. So I'll just give you the answer. Then we're going to use Hazen Williams, and then we're going to do Mannings. And just compare them all. So from Darcy-Weisbach, and this was what we did last time, we got Q is equal to 0.56 cubic meters per second. And then let's go ahead and do it with those two equations together. So first we'll do Hazen Williams. And instead of going through all those steps like we did with the kind of Darcy-Weisbach and energy equation approach, we're just going to go ahead and plug a bunch of numbers in and calculate it. So our Hazen Williams equation is velocity is equal to, here we are in metric, so it's 0.849 is our outer coefficients. We have our Hazen Williams coefficient, which we'll look up in a table. We need hydraulic radius, so the 0.63, and then our slope or friction slope to the 0.54. So first, let's look up our Hazen Williams coefficient, and I've got it printed out for you. So second page of this handout. Table 3.2 in your book. And we say we have cast iron. We don't really give an age. We're assuming it's a new construction. So let's go with the new cast iron value. What was that? 130. So new unlined cast iron pipe, 130. Okay. Let's do hydraulic radius. Hydraulic radius was, we just said D over 4 for a pipe. So that would be 0.125 meters. And then our slope, which is our friction slope, unless otherwise specified. And that is our delta H over L. So what's that going to be? Yeah. So our delta H is just the difference in the elevation of these two water surfaces. So 10 meters over our length, which was 700 meters. And that gives us 1/7 or 0.0143. So now we just plug everything in. Units are meaningless with empirical equations because in this case, we would have meters to the 0.63, right? That doesn't make any sense. So we just kind of ignore units for the most part. But we ignore the fact that like it's dimensionally inconsistent, but we do have to track, right? Because we have to put in, this is going to be meters, right? And this is going to be meters per meter. So we do have to keep track of what values we're plugging in. That's where empirical equations can get really confusing. It's like, okay, what units am I putting in? Is it inches or feet? And what am I getting out? Because you can't actually track the units. Okay, so we end up with a velocity of 2.71, or sorry, 3.01. And then that gives us a Q. If we do times d squared, pi d squared over 4, we get a Q of 0.6 cubic meters per second. So we'll compare it to this. We'll kind of say like this is going to be the quote unquote true value from the theoretical Darcy-Weisbach equation. And this is our approximate. All right, let's do it with Mannings real quick. Let's go look at our table. So I'll just write the equation out. V is equal to 1 over n. Hydraulic radius to 2/3. Friction slope to the 1/2. N from table 3.3. And we say we have a cast iron. We got a range there, right? Kind of depends on if you want to be over or under conservative, depends on your design. In this case, let's just pick a middle value, which would be 0.013 for cast iron. And we've already calculated these values from before, so we can just plug those in. Oh, you know what? I used a different value. So just like we did for Hazen Williams, we assumed a new pipe. So we'll assume the smoother conditions for a new pipe. So we'll take the minimum value. And then we'll say V is equal to 1 over 0.011 times 0.125 to the 2/3 times 0.0143 to the 1/2. And then our Q, if we multiply pi d squared over 4, is 0.53 cubic meters per second. So just to summarize, we got Darcy-Weisbach, which gave us 0.56 cubic meters per second. We had Hazen Williams, which gave us 0.60. And then we had Mannings 0.53. Is that a big difference or a little difference? You could calculate the kind of percent error if we assume that this is the actual value and calculate the percent error. So 0.04 versus 0.07 cubic meters per second divided by 0.6. Is that about 10% or so error? A little bit under 10% error. So is that important or not? That's really up to your design question. This is just a quick and dirty tool we can use, maybe for back of the envelope types of calculations. We also need to note one other thing, and this will be a last point before we take a quick break, is that if we go back to how these equations were originally made, we had data which had scatter to it, and we fit a line. So say this is velocity and these are independent variables. What we're doing here is we're plugging in our independent variables and sticking out a velocity, right? Just call it V naught, whatever. So one value. We'll learn in statistics that that's basically the average value of, if you think of, here's the range of potential values based on your data distribution. This value is just kind of the mean value that you would expect given that distribution of data of our independent, or of the velocities that could happen for a given set of independent variables. So there's uncertainty here, and this could be, you could, for example, say you could make a 95% confidence interval, which we'll do in statistics later. Gina's already had this and been exposed to this. Empirical equations typically don't report that. Sometimes they do, it'll give you some error associated with that, but just know that underlying all these empirical equations is noise, is uncertainty, and understanding that when you get one value, there's a lot of error potentially associated with that.